Hi everyone, welcome back. This mini lecture will be about Bloch's theorem. So as usual, let's pause and remember where we are in this course. We started by thinking about the Drude model, which you remember is a model for electrons in a metal. It considers classical electrons that collide with ions. The electrons are free and independent, and they're in equilibrium. Remember that during the rest of this course, we're going to gradually dismantle these assumptions one by one. We already relaxed the assumption that the electrons must be classical when we allow them to obey Fermi-Dirac statistics. We arrive at the Sommerfeld model. Then we decided that we would relax the free electron assumption. Now we're on our way to investigating what happens when we allow the electrons to always interact with the lattice of ions. So our first step in that direction was to consider the properties of crystal lattices. So we talked about lattices themselves as well as the reciprocal lattice. Let me just briefly remind you of the reciprocal lattice. It's a set of vectors k such that e to the I k dot r is equal to 1 for all vectors r in the Brevet lattice itself. If you like reciprocal lattice vectors big K, define wave vectors associated with the Brevet lattice itself. The reciprocal lattice vectors, as we saw, are perpendicular to lattice planes. We also talked about X-ray diffraction. We remembered the Bragg condition for constructive X-ray interference, n lambda is equal to twice d sine theta, where d is the distance between the lattice planes of a sample. We also derived the von Laue condition for X-ray diffraction, which is that the change in wave vector between the incident and detected X-rays must be equal to a reciprocal lattice vector in order for constructive interference to occur. Now, X-ray diffraction is obviously very important for the characterization of solid-state materials. It also turns out that this notion of constructive interference really is a handy way to think about things like energy gaps. So today we'll start our journey toward our discussion of band structure and energy gaps and so forth. And we'll talk about Bloch's theorem. So the key thing to remember is that the underlying question we're thinking about right now is what happens to the electrons when we allow them to interact with the potential of the ions all the time. And I'll put allow in quotation marks because, of course, they actually interact with the potential all of the time. It's just that we are now considering this to be the case. So the main feature of this problem, which is obviously quite hard, that will allow us to make some headway is that the potential is periodic. So in particular, we mean that if capital U is the function describing the ionic potential, U of little r plus big R is equal to U of little r for all big R in the Brevet lattice. So our game, of course, is to solve the Schrodinger equation. in particular, we're looking for the wave functions psi and single particle energies E that satisfy the Schrodinger equation with now the ionic potential. Bloch's theorem states that the solutions to the Schrodinger equation with the periodic potential have the following form. So they have two quantum numbers, n and k. The wave function is a plane wave, e to the I k dot r, times another function, which depends on position as well as the two quantum numbers n and k. And this function u has the periodicity of the Bravais lattice. Which is to say, u of little r plus big R is the same as u of little r, again, for all big R in the Bravais lattice. So we'll prove Bloch's theorem one way in this mini lecture and another way in the next mini lecture. For now, maybe the most important thing to remember is that Bloch's theorem says that eigenfunctions of the Schrodinger equation for a periodic potential are plane waves times periodic functions. So the cartoon picture to have in your head for one of these eigenfunctions looks like the following. So let's plot u as a function of r. Okay, so it's some periodic function, and you might imagine that there are spikes in the value of this function where the electrons would be sitting on top of the ions. You can imagine, let's say, a plane wave that looks something like this. Now, the overall wave function will be the product of these two. I'm clearly plotting the real part of the plane wave here. So I'll plot the real part of the total function. So it's the product of these two, this periodic function u and the plane wave, which I've drawn in dotted lines. The overall wave function then might look something like this. Okay, and you get the idea. So it's a plane wave times a periodic function. Okay, there's an alternate form of Bloch's theorem, which we can understand by the following. So if we notice that psi of r plus big R can be written in the following way. Here I'm using the first form of Bloch's theorem. So I broke apart the plane wave into the product of two plane waves here. But this is the same thing as e to the I k dot big R times u at little r times e to the I k dot little r, where we use the fact that this function u has the periodicity of the Bravais lattice. So I can write now the equation the following way. It's e to the I k dot big R times psi of little r. So this is an alternate statement of Bloch's theorem. It says that if I displace the wave function by a vector in the Bravais lattice, I can find a wave vector little k such that that displaced wave function is e to the I k dot big R times psi of r itself. So these are two equivalent statements of Bloch's theorem. We will prove Bloch's theorem in one way in this mini lecture. The first proof is based on a set of formal quantum mechanical arguments. The second proof, which you'll see in the next mini lecture, is based on the Fourier expansion of the Schrodinger equation and the eigenfunctions. So let's prove Bloch's theorem. So let's define a translation operator. T, which depends on a vector R, such that the translation operator acting on some function f of R gives us that function displaced by big R. Okay, so let's then note that the translation operator acting on H psi, where H is the Hamiltonian, psi is the wave function, is equal to, well, H at R plus big R times psi at R plus big R. But the Hamiltonian is periodic in the Bravais lattice by construction. So we'll say that this is equal to H times the translation operator T acting on psi itself. So this last equation means that H and T commute. This in turn means that I can find a simultaneous set of eigenvalues for H and T. So this is a handy fact. Let's also ask what happens when we apply two successive translation operators to the same function. So let's compute TR prime acting on psi. Well, that's equal to psi displaced by both R and R prime. You can see that it doesn't matter the order in which I apply these translations. And moreover, it's the same thing as a single translation by the sum of the displacement vectors. So now what we can say is that the set of all translation operators T for different vectors, along with the Hamiltonian, form a commuting set. So we can find a simultaneous set of eigenvalues for the Hamiltonian, as well as all of the translation operators T of R. So to be specific, we can look for eigenvalues E and eigenvalues C, which depend on R, for the same wave function psi. Moreover, since the product of translation operators is equal to the sum, moreover, the product of the translation, because the product of the translation operators is equal to a translation by the sum, we can say that the eigenvalue C corresponding to R plus R prime is equal to the product of the eigenvalues C of R and C of R prime. Good. So let's suppose that the AI are primitive lattice vectors. Then let's write C of AI, so the eigenvalue corresponding to translation by one of the primitive lattice vectors AI, as e to the 2 pi I xi. Now, this is, in fact, a general statement because the xi can be complex. So even though it looks like this should just be a phase factor, at the moment, this is a completely general way to write down this eigenvalue. So let's also write big R, a vector in the Bouvet lattice, in the usual way. It's the sum of the primitive lattice vectors with different integer coefficients ni. Okay, so using this fact, as well as the concept that we can write any vector in the Bouvet lattice as the sum of primitive lattice vectors with different integer coefficients, along with the fact from the previous screen that the eigenvalue of the translation operator of a sum of translations is equal to the product of the eigenvalues for the different translations in the following way. So I can write the eigenvalue for a translation by a Bouvet lattice vector as the product of the eigenvalues for the translations by the separate primitive lattice vectors. So I use the fact that the eigenvalue corresponding to a sum is the product of eigenvalues. And we also used this expression here for the individual eigenvalues associated with the primitive lattice vectors. Okay, so I can write this now as e to the 2 pi I n1 x1 plus n2 x2 plus n3 x3. That's again using this expression up here. x1, x2, and x3, remember, essentially describe the eigenvalues for the translation operators of the primitive lattice vectors, the AI themselves. So this clearly means that we can write the eigenvalue for displacement by a lattice vector R as e to the I k dot R, with k is equal to x1 b1 plus x2 b2 plus x3 b3. Let me rewrite this on this screen here. Where the bi, of course, are the primitive vectors of the reciprocal lattice. Remember that AI dot bj is equal to 2 pi times Kronecker delta of I and j. So using this relationship, you can very easily see that we can express the wave vector here which describes the eigenvalue for translation by a Bravais lattice vector in exactly this form. Okay? So all said and done, now we can see that applying the translation operator to the eigenfunction psi, which gives us psi of little r plus big R, is equal to the eigenvalue corresponding to displacement by that amount times psi at little r, that we've just shown that we can write this eigenvalue is e to the I little k dot r times psi of r. Okay, so this is of the Bloch form. Notice that you may have assumed that the little k values are real, but up until this point, we have not yet specified what they should be. What determines what they are? Of course, boundary conditions do as usual. So let's now talk about that. So as before, when we talked about Sommerfeld theory, we are also going to work with periodic boundary conditions. And the reason, again, is, of course, that this emphasizes that we're interested in working with the bulk properties of a crystal. We're not so interested in the properties of the surface. So before we worked with a cube in Sommerfeld theory. Now we're talking about more general arrangements of atoms. So we're going to work with a volume commensurate with the unit cell of the Bravais lattice. So in particular, we'll require that psi of r plus NiAi is equal to psi of r. So here I can be 1, 2, or 3. And the Ni are integers. So let's set capital N equal N1, N2, N3. This is equal to the total number of primitive cells in the crystal. So if you like, the capital Ni describe the extent of the crystal we're thinking about along the directions of any of the primitive lattice vectors. So let's apply Bloch's theorem to our boundary condition. So if we displace the wave function by NiAi, we know based on Bloch's theorem that we can write this as e to the I Ni k dot ai times psi at r. So we're using the version of Bloch's theorem which says that if we displace the wave function by a Bravais lattice vector, indeed this is one, the result is a plane wave, here it is, times the wave function at the original location. So you can now very clearly see, if we reference our boundary condition up here, that we must have e to the I Ni k dot ai is equal to 1. So you can see that again, and as usual, applying the boundary conditions will restrict the allowed values of k. So if we set k as x1, b1 plus x2, b2 plus x3, b3. Here the x's are not restricted just yet. Then using the previous equation we wrote down, we can see that e to the 2 pi I ni xi is equal to 1. Again, that's using the fact that the dot product of ai and bj is equal to 2 pi delta ij. This means then that ni xi, the product ni xi should be equal to something we'll call mi, which is an integer, which means that xi, the components of this wave vector, should be equal to mi over ni. So mi is an integer, ni is the total extent of the crystal along the ith primitive vector direction. Okay, so the general form of the Bloch wave vector then is following. Let me get back to my Zoom screen. Is k is equal to sum from I goes to 1 to 3 of mi over ni times bi, where of course mi is an integer. Okay. Let's ask about the volume of k space per allowed value of k, just like we did before. If you like, the volume is the volume of a parallel pipe head with edge bi over ni. And using a well-known formula from geometry, the volume of that object is b1 over n1 dot, the cross product of b2 over n2 times b3 over n3. This is 1 over capital N times b1 dot b2 cross b3. This is the volume of the reciprocal lattice primitive cell. If this is a little bit confusing, perhaps it's helpful to think about a simple cubic lattice where the reciprocal lattice is also a simple cubic. Then b2 cross b3 would, for example, be y cross z, would be b, the length b2 would be 2 pi over 8 over n2, y hat cross 2 pi over a over n3 cross times z hat, right, rather, which would give you something along the x direction. This dot product then would simply be a multiplication of the magnitudes of these two vectors. So what this is telling us is a somewhat interesting fact, which is that b1 dot b2 cross b3 divided by the magnitude delta k is equal to capital N. It's equal to the total number of sites in the crystal. So the first Brouillon zone, the primitive cell of the reciprocal lattice, contains an allowed number of wave vectors equal to the total number of sites in the crystal. This actually foreshadows one of the important themes of this course, and probably one of the more challenging to understand themes, which is that essentially all of the information is contained within the first Brillouin zone of the reciprocal lattice. And again, that's essentially because there are an allowed number of points in K-space in the first Brillouin zone in the primitive cell of the reciprocal lattice equal to the total number of atoms in the crystal. All right, so we'll continue in the next mini lecture with another proof of Bloch's theorem, which emphasizes its importance from a slightly different point of view.